All right, here we go. This should be lecture number 14. Um, we had a physicist named Niels Bohr, and he was able to adopt Planck's assumption of these quantized energy levels and explain line spectra in what we now call Bohr's model of the atom. So there's certain postulates here. So we have postulate number one. So he said that electrons in an atom can only occupy certain orbits. And his idea of an orbit was just like a circular path, like the Isotopes baseball team, the kind of like the emblem you see, where it's like the old timey symbol of an atom, where there's like a little nucleus and you got the little ovals kind of floating around, swinging around it. That's what he's talking about. This is the Bohr model of the atom, where the electrons are just in these rings going around. Number two, that the electrons that are in these orbits will have specific allowed energies. So there's only certain energies that are allowed in the atom. Right, so it's quantized and set to particular energy levels. Energy is only absorbed or emitted in such a way to move an electron from one allowed energy state to another, and that energy is defined by E equals h nu. So these pictures on the side here, don't freak out. This is from my AP class, so don't look at that and like go, oh my gosh, and start having a heart attack. It does look kind of scary, right? But it's not that big of a deal. This is showing the different transitions. So the electrons, if it's moving from here to here, that gives off a photon, or here to here gives off a photon. These big arrows, these are high energy transitions. So there's a line spectrum in the ultraviolet. So we can't see it with our naked eyes. What I showed you before, the 4 lines, that's this. It's called the Balmer series. That's these 4 lines right here are what you're seeing. There's also another one in the infrared, right up there. But remember, in the visible spectrum of hydrogen, there was 4 lines. There's a red line, a green line, a blue line, and a purple line. So could you look at this and figure out which one's which? Like, those all have different energies, right? Like red light, green light, blue light, purple light. The highest energy light is purple, right? Remember I told you like ultraviolet stuff, that's bad for you. It's because it's high energy. So the greatest energy change here, right there, that's actually the purple one. This is the blue one. This would be the green one. This smallest energy jump right here, that would be the red line. So in the visible spectrum, those are the 4 transitions you're seeing. So the transitions of the electron from the 3rd shell down to the 2nd. So that's the red line, and then so on and so on and so on. Pretty cool. All right, so Bohr model, it fits hydrogen really, really well. All right, it postulates only these certain allowed circular orbits, and it's all swell. The next little thing, you're like, don't worry about this one too much, but as the electron gets more tightly bound, its energy gets lower and lower and lower. And so just kind of as a reference point, they say that an electron that is free, a free electron, like not stuck onto an atom, we say that that's 0 energy. So that's like a reference state. So what's less than 0, it's going to be negative, right? So as the electron gets closer and closer to the nucleus, energy is released. So if you started off at 0 and then you're releasing energy, you're going more and more negative. So if you do see that in a future class, that's all the stuff that's going on there. All right, so Bohr model, really cool. Works great for hydrogen, but it's wrong. It only works for hydrogen. So that means, we got to go back. So remember when I talked about the whole scientific method, you make models and then you do these predictions and this, that, and the other thing. This is one of those cases where it's like, okay, works great for hydrogen, but then when they tried it on not hydrogen, it didn't work. It didn't completely, it's not totally garbage. I mean, it's not like, it's junk. There are some good parts of it still, but it needed to be tweaked. All right, so there needs to be some refinements. And one of those things is, electrons aren't going around in nice, predictable circular paths. So let me tell you about something really crazy. So let your brain buckle up for this. The wave nature of matter. There is a graduate student, Louis de Broglie. And yes, I say de Broglie. I've heard de Broglie. I've heard de Broglie. All sorts of crazy pronunciations, but I'll say de Broglie because it's just how I'm used to saying it. But he thought that if light can act like a particle, right? So I just showed you light can be treated as a particle, a photon, a little nugget of light. So he thought if light can be a particle, can particles be like light? Could matter show wave properties? And he was able to come up with this equation here. And it was later shown that electrons, they actually do display wave properties. It's crazy. In fact, that's why electron microscopes work. So if you ever look up electron microscope pictures and they have 1 million times magnification, it's because electrons have a wavelength and it's much, much, much shorter than visible light. So you get much higher resolution. So it's crazy. It's matter, but these little tiny pieces of matter, they have a wavelength. It's nutty. Now, waves confined to a certain space can only have certain frequency. They're called standing waves. All right, so standing waves, kind of like on a guitar string, which I'm going to show you in the next slide. But the electrons act like a standing wave confined around the nucleus. So let me just kind of tell you what a standing wave is really quick. So like on a guitar, right? Here's an unplucked string, right? The guitar string is locked down at both ends, right? So when you hit it, all these waves go rattling through it, but only certain ones persist. Those are like the natural frequencies, the resonant frequencies. So one of these things I could have where basically the length of the string is half the wavelength. So this whole entire wave would actually go off the picture here. The length of the string here is 2/2 of the wavelength. This length, 3/2. So you see it's going to multiples, like 1/2, 2/2, 3/2, 4/2, and that's kind of cool. So what does this have to do with electrons in a nucleus? All right. Imagine you got a nucleus in here, and we're only doing this in 2 dimensions. So the reality is it's 3 dimensions, so it gets a little bit weirder than this even. But imagine you have a wavelength. So say this is the wavelength of my electron, right? If I'm this particular distance from the nucleus, I can fit exactly 4 waves. So 1, 2, 3, 4. And I'm exactly where I started, and then it just feeds back into itself. So 4. If I move a little further out, if I go to a slightly larger radius, now I can fit exactly 5. So if I start right here, that's 1, 2, 3, 4, 5. All right, cool. If I'm at a distance kind of in between, there's a mismatch. It'll go around, but it's not going to go back to where it was, and you get what's called destructive interference. It won't happen. So the wave can either be here or it can be here. All right, so the closer the electron is to the nucleus, the lower its energy is going to be. All right, so this would be a higher energy orbital, and this would be a lower energy, orbit. I haven't told you about orbitals yet, so I'll take that back. But that's what's going on. We got these weird standing waves, and I'll show you a video that shows like water droplets levitated in an acoustic field, and it gets kind of crazy, but it's really cool, and it's what I've always kind of thought that the electron orbitals would look like floating around a nucleus. Kind of crazy stuff. All right, couple more. All right, the uncertainty principle. When we make a measurement, I can't honestly think of a measurement that doesn't involve photons. And you're thinking, oh, that's crazy. Like even when you're measuring a graduated cylinder, like you did on our density lab, you needed photons. Like light needed to hit, the water that was in the graduated cylinder, and then it bounces back into your eyes. Like that's how we detect everything. Even with like fancy schmancy detectors, it's usually photons of some particular wavelength that are interacting with matter and bouncing into a detector. And that's how we see things. That's how we measure things. The deal is with electrons is that they're so small and they're so skittish. And I've already showed you now that photons have energy, and that energy will knock the electron off course. And so if you try to measure what an electron is doing, you change what it was doing. It gets a little weird. So there's the Heisenberg uncertainty principle. So way back when Breaking Bad was on TV, I had a student like freak out at this point in the lecture. Like, wait a minute, that's a real thing, Heisenberg? And I'm like, yeah, of course it's a real thing. That's what's kind of funny about the show. So in case you don't know, Breaking Bad's about a chemistry teacher who ends up making meth and becoming a meth dealer, and it's a whole crazy thing. And it actually happens in Albuquerque here, so it's kind of cool to watch. But yeah, it's a really sketchy, uncertain profession, and so that's why he's going by Heisenberg. So kind of a good bit of nerd humor there. But the Heisenberg uncertainty principle basically says that it is impossible to simultaneously know the location and the momentum of an electron. And this says velocity, but kind of the same thing, sort of, for this thing. So the direction, where it's going. So where it is and where it's going. So it's impossible to determine the exact location and then where it's going. So think of it that way. The more you know one, the less you know the other. That's the really kind of oversimplified version of it, but that'll work for our class just fine. So the more we know about its location, the less we know about where it's going. And the more we know about where it's going, the less we knew about its initial location. So it gets weird. It gets really goofy. So along comes a guy named Erwin Schrödinger, and he developed this mathematical treatment where it took into account the wave and particle nature of the electron and dealing with probability and all this crazy stuff. And this is known as quantum mechanics. And it gets really, really crazy. But we're not going super deep into this stuff. But if you go off to college and major in chemistry, you'll get to take a class called physical chemistry and solve the actual quantum, the Schrödinger equation. My brain's going dead now. But yeah, it's a crazy thing. And you get spherical polar coordinates, and all sorts of just shenanigans going on. It's nuts. But we're going to get a little bit into quantum mechanics for the next video. I will see you then. See ya.